Today we're going to talk about boundary conditions and equilibria. Okay, so what do we mean by boundary conditions? So recall from normal ODEs, we have this thing called an initial condition. And that was able to determine a unique solution to ordinary differential equation. DE. Okay, so now we're talking about partial differential equations. And we call those PDEs. Okay, so PDEs, we need a few more things that go beyond initial conditions, and that's what we call a boundary condition. And so let's go back to our particular example, the one partial differential equation we know, which is the heat equation. We can write it as the time derivative of the temperature is equal to the thermal diffusivity times the second derivative, spatial derivative of the temperature. So again, we're doing this in 1D. We think of it as a long bar or rod like that, from 0 to L. All right. So we knew from this, from before, that at any point x equals a, say, we can define this flux, which is the thermal flux, or the heat flux, at x equals a. And we use Fourier's law to state that the flux has to be equal to the negative, spatial derivative times the negative spatial derivative of the temperature times this thermal conductivity constant, capital K0. All right, so we use that law, and that worked as long as we were inside. So this applies inside the rod. So now what we want to do is, what happens then on the ends? Put a question mark there. So on the ends, we can think of again, we have no heat transfer up and down on this. We consider this as being insulated. Both on the top and the bottom there. But there could be a temperature flux at the ends of the rod. So we're going to discuss a couple different cases of what we can do. We want to apply, so basically the goal is apply a similar conditions to Fourier's law, things like Fourier's law, to the boundaries. And that is, we're going to apply a physical principle, a physical rule for how temperature or the flux, the thermal flux, is dictated at the boundary. and that means x equals 0 and x equals L. Okay, so let's think of a few examples here. So in fact, we're going to go over 3 broad categories of what we call boundary conditions, BCs. Okay, so the first one is what we're going to call a fixed temperature boundary condition. And this goes up over the technical term, and you'll hear this very often. It's called a Dirichlet. Got to spell the guy's name right. It's called a Dirichlet boundary condition, named after a fellow named Dirichlet. And what we mean by this is the modeling situation where we would apply a fixed temperature boundary condition is when we have a rod, x equals 0, x equals L, with very large heat reservoirs. On either side. Think of it as so large, we can have another one on the other side like that. We can literally say that this is U0 of T on this side, the temperature in this very large heat reservoir on the left, and a U of L of T on the right. And these are, and what the assumption here that the rod is so small that the rod temperature, or maybe the energy content of the rod, does not influence these reservoirs. So these reservoirs could be hot or cold, and the rod could be very hot or very cold, but it doesn't matter because this rod, the actual energy content inside of the rod is so tiny it does not influence these temperatures. So what we say then is that, again, the solutions we're looking for, the kind of functions we're looking for U of x comma t style solutions to this heat equation. We can write the heat equation over here again. But we're going to add to this heat equation some extra conditions. The boundary condition will be as follows. It'll be that U, so again we want to find U of x comma t, subject to the boundary condition that at x equals 0 t, we have these functions U of t and U of x equals L of t, comma t, is equal to UL of t. And the idea here is that these are set functions. They set the temperature at the boundaries. And basically it is, no matter how hot this bar is or how cold it is, whatever temperature it is outside in these large heat reservoirs, it fixes the temperatures at each end to be U0 and UL. And they could be functions of time. All right, so this together creates a better picture of what's going on. So again, this isn't the case that the rod is so small that the energy content of the rod is inconsequential to these reservoirs. Okay, so that's the first category of boundary conditions. So now let's talk about two. The second category will be one of a flux condition. So again, we have this bar, and we know that there's a flux that can be determined at every point inside the bar. And now on the edges, we're going to say that that we're actually going to say whatever this reservoir is out here, it may not control the temperature at the ends, but what it does is it controls how much heat is being put in or taken out at each end. So we can think of this as a condition. We know from Fourier's law that inside the bar, the flux is equal to some negative k0 partial of u partial of x. All right. So in general, though, that depends on inside the bar. But outside the bar property, we don't need to use that constant. We can just set phi of x equals 0 of time. We can just set that to be the partial with respect to x evaluated x equals 0, and a partial x equals L of t is equal to the partial of u with respect to x equals L. So again, now these are the defined functions, or the set. So these conditions don't set the temperature at the bar ends, but they do set the heat flux, or the energy flux, into the bar and out of the bar on both ends. So this is a different kind of condition. And this has another name. It's named after another fellow called Neumann. After Jean von Neumann. And it's called a Neumann boundary condition. Okay, so there we go. And now these are the two main conditions: the flux condition and also just the fixed temperature condition. So let's talk about the final one, the third one, which is called a hybrid boundary condition. And this also goes by the name of another fellow called a Robin boundary condition. Okay. So what is a hybrid condition? And this is actually, we actually think of it as a mix of temperature and flux. Temperature and flux boundary conditions. So what this looks like is that what we have is a situation like this. So let's just look at x equals L, this end. We have a large heat reservoir just like before, and we have a temperature at this end. But let's say now that we don't, this temperature, the temperature in this large heat reservoir isn't so large, that we have some more complicated dynamics going on. So let's say that there is some flux. Let's say we can think of this as very hot, just to make a concrete example, and this is a very cold outside. And so again, we're going to have some heat flux coming out of this end. But let's say what it's going to do is it's sort of going to heat up the air. If we think of this as a fluid, like air, it's going to heat up the air right around there. And that's theoretically what it's going to do, is sort of slow the transfer of heat, because the air right around the bar end will be heated up. But we'll also put a fan. Again, this is the idea. We have a little fan that whirs around, and it's going to be pushing air through. And so this air will be warming up, but it will also be leaving. And what's going to lead to is that this temperature in the outside won't change much. The average temperature out here won't change much, but it does take some time for that temperature to leave There is a gradient of temperature within the reservoir. So what we're talking about here is a condition where the flux depends on the temperature difference between the reservoir and the end temp, U of x equals L T. Now obviously we can do another one on this side, but once we do it on this side you can get the idea here. And so we can write this down as follows. We'll say then again the flux from Fourier's law was negative K0, the partial of U with respect to x, and we're going to evaluate it at x equals L. Okay, sounds good. We're going to say that this flux here is going to be determined by the difference between the temperature set outside of the reservoir minus the temperature at the end. Of our rod, the temperature right there. All right, so there's the temperature difference. And of course this again is that conductivity constant. And we're going to evaluate this at x equals L there. And this, we're going to call this is just going to be a catch-all transfer coefficient. So what is the meaning of H? Now H is again a property of both it really is a property of the material interface It's the property of the material interface at this point. It's the property of how the fluid is circulating through this reservoir. It's a property of a lot of things about the entire system, but we're folding that all into this one constant. Okay, so so when I said that this is a hybrid boundary condition, we can see clearly that this condition here, this hybrid, contains both previous BC types. So for instance, if I set H to 0, what we get is an insulated I shouldn't say it contains both BC types, but it does contain a large family of them. So it creates, if H is equal to 0, it creates an insulated boundary condition. Here we have the flux, the heat flux through the end will be 0. Okay, and that basically means that there's essentially no transfer of heat. So that transfer coefficient being 0 means that there's no transfer of heat to the outside. Okay. Now, take the other example. What if we take H goes to get really big? And this is analogous also to, so in this case, we could also put K going really small. But the idea is that it's the relative magnitude of K0 to H. So which case is it? Depends on what perspective you want to take. But let's think of it as H going to infinity. In which case we're saying is that transfer coefficient is very, very large. It's so large, in fact, that it dwarfs the actual flux at the very end of the bar. That's not really the issue. It's the interface is very, very strong. And that means that this interface is so effective at taking heat away from the end of that rod that effectively if this is cold out here, it means that the end temperature is going to be exactly equal to the outside temperature. So that corresponds to our Dirichlet conditions or our fixed endpoint conditions. It implies then that it's UL of T, our set outside temperature, is equal to our end temperature. All right, so that's our Dirichlet condition. again. Okay, so there's our three boundary condition types. So from these three boundary conditions, we can model a lot of the way that heat transfer can work in a real system. So what we want to do now is switch gears a bit and actually do what you want to do with a partial differential equation, which is solve this PDE. So we want to solve the heat equation. All right, so and now we want to solve it with different boundary conditions. We're going to need those boundary conditions to solve this PDE. And so what we're going to do, though, is we're not going to solve this thing. So again, we want to find, in general, we would want to find u as a function of both time and space. Usually we write space first, x comma t. But what we're going to do first is we're going to look for equilibrium conditions. Or equilibrium solutions. So that means in the case that u of x comma t is actually just u of x. All right, and this is the condition that the partial derivative of u of t is equal to 0, is equal to k u. So we can write this as k u double prime is equal to 0. All right, so let's look at that first boundary condition. We'll look at the fixed end, fixed temp conditions. So we'll give an example of u at x equals 0 is equal to T1, and u at x equals L is equal to T2. So two different temperatures on two different ends. We have these giant heat reservoirs on either side, and they effectively set the temperature at the ends of our bars to be they are so strong, the coupling between the ends is so strong that the temperatures are set to be T1 and T2. All right, and then we want to find solutions to the equation then. K u double prime is equal to 0. So clearly k doesn't matter. We can divide k out of there. It's just fine. So we really have just u double prime is equal to 0. So this is a very standard or a very simple linear differential operator. This is actually an ODE, right? Notice how we've taken a PDE, and by looking for an equilibrium solution, we knock out one of the partial derivatives in time, and we're left with only a partial derivative in space, which we'll just call u double prime. So in this case, the primes are with respect to x, just so we're not confused. All right, so this is a common practice in a lot of our solution methods of PDEs, is we find ways to turn partial differential equations over different variables into ordinary differential equations in single variables. So here's our ODE. We want to solve that. How do we solve that? Well, there's two different ways. We can think of it as we want to find the homogeneous solution of LU is equal to 0, where L of u is equal to u double prime. So we know already that u of x then has to be of the form c1x plus c2. All right, what's another way where these are these undetermined constants c1 and c2? The other way is to just do a straightforward integration. So what we can do is go u double prime is equal to 0. Take the antiderivative of that, and we get u prime. And that has to equal the integral of 0 is, of course, just a constant, c1. And then we take the antiderivative of that again, and we get u of x is equal to c1x plus c2. All right, so there we go. There's our nice solution to this problem. the next thing we need to do is apply a boundary condition. So in this case, u of x equals 0 is equal to c1 times 0 plus c2. And we know that was equal to t1. So we put t1 in there, and of course we find out that that is equal to c2. Now u of x equals to L, we write that as c1 L plus, and now c2 is equal to t1, which is a known, which is a given temperature. And that's supposed to be equal to t2. So that means that c1 is equal to t2 minus t1 all over L. So our solution, I should call it an equilibrium solution. And I'll call it u eq of x is equal to t2 minus t1 all over L quantity times x plus t1. All right, so what is this? We can plot the solution. Of course, this is linear. And so there's 0, there's L, and if here is t1, and I'll just give an example, and that's t2, that's what it looks like. It's just a linear graded temperature between the top and the bottom. So this is a good example of perhaps maybe we can, this is a model for let's say the wall of a house where in the wintertime it might be cold out here, and this is the inside, and the inside of the house is warm, right? And so we can imagine that if this wall was a homogeneous medium, let's say it's brick or something like that, where it's more or less a homogeneous medium from outside to in, then the temperature should just be a linear decline. So that gives you a realistic result out of a simple PDE. So that's nice. So now what we want to do is talk about the other boundary condition type, which is that of an insulated rod. So let's do now this insulated ends. So this corresponds to, again, we have our partial differential equation. And that's equal to 0 because we're looking for equilibrium solutions. So that time derivative is 0. So what we have is u double prime, where the primes are derivatives in x, is equal to 0. But we have we have the boundary condition, these auxiliary conditions that help us determine our solution. A view of the partial derivative with respect to x evaluated at 0, and the partial derivative of x evaluated at L are both equal to 0. And that means there's no flux at boundary BDY. Okay, so how do we solve this equation? Well, it's very similar. We know the solutions to this equation are of the form u of x is equal to c1x plus c2. So here's the issue, though. We know that the derivatives at the boundaries are 0, and that means that if I take the derivative of this thing, it's going to be equal to c1, and that's going to be equal to 0 at the boundaries, which implies, though, then c1 is equal to 0. So u of x is equal to c2. So both of the boundaries are 0, and that means that c1 is 0, but that means that c2 is yet unknown. So what do we do to figure out this unknown constant? These boundary conditions did not help us find c2. So we need to appeal to what we knew about ODEs. We had initial conditions. So what do we mean by initial conditions? So when we started, we wanted to find u of x comma t solutions, right? Solutions involving a time variable. All right, but then we switched and just talked about equilibrium conditions where the time derivative was 0. In a sense, what we're finding is, but what we assume here in this case, if this is our equilibrium solution, we assume that the limit as time goes to infinity of our whatever our solution was, it's going to be equal. It's going to asymptotically approach our equilibrium solution that's only in x. So we assume that. All right. And so now what we do is we bring in initial conditions. And initial conditions we can set as a third condition on top of our boundary conditions. So we have our partial differential equation. We have a set of boundary conditions. And now we have one more condition, which we'll call IC. And that is u of x t equals 0, comma, is equal to f of x. That's the initial temperature profile of our rod at time equals 0 when we start evolving our system forward according to that PDE. So what does that look like? Well, certainly, what are we going to do then? So what do we know about the no flux of the boundary? Because it's insulated on all aspects, we know that this rod, there is no energy loss for all time. So the total energy is going to be equal to, remember, the specific heat times rho times u integrated from 0 to L dx, right? And so we know there's no energy loss for all time, and that means the derivative of this is equal to 0. And it also means then at time equals 0, we do know what u is. It's going to be, so the total energy is going to be, so at time 0, the total energy is going to be integral from 0 to L of our specific heat, our density of mass of our rod, times f of x, right? Because that's what our initial condition was, dx. But we also know, because there's no energy loss, and we know that the total energy doesn't change for all time, we also know it has to be the energy at the end. So we know the equilibrium energy was C2, our unknown constant. So we can write that down. That's going to be integral of 0 to L. So this is at time going to infinity. It's going to be, again, the specific heat times the mass density times C2 dx. All right, so we can jettison these terms here and set them equal to each other because they're both the same. I'm going to write it up here then. And that means that we have, and let's say I just write that again. I can write that as C times rho times C2L. So we can cancel the C and rho terms and determine then that C2 has to be equal to 1 over L integral of 0 to L f of x dx. And this, if we remember from our basic calculus, is the average temp of the rod. Okay, so again, what we think about is at t equals 0, we have some function, 0 to L. Maybe the rod temperature is like this, right? And it's going up and down and all over the place, but there's some sort of average temperature. All right, and so as time goes forward, and it heads towards infinity, we go from 0 to L. The end temperature will just be the same as the average, but all of the bumps, all of the high points and all the low temperatures will all get smoothed out and eventually converge towards the average temperature. So this is an important concept in understanding how the heat equation is working. So the heat equation is taking any kind of variation in temperature over this bar, and provided no energy is lost through the system, what we end up getting from this is that the end temperature of the bar is going to be homogeneous. It's going to be a constant value, but it's still going to be equal to the average temperature. So the idea that we're converging towards an average, everything becomes averaged, is an important concept of heat transfer, and that will be our lesson for the day, essentially. So let's just write down a few things real quick. Let's write down a few things real quick. So what we had here was a partial differential equation. I'm going to call it a PDE problem. Contains a few ingredients. It contains a PDE. So in this case, the heat equation, which is partial of U with respect to T equals K, second partial with respect to space. All right? But then it also contains those boundary conditions. All right, so that's the first ingredient. Is heat equation is the actual PDE. The second is boundary conditions. And remember, there's fixed, there's flux, and then there's those hybrid. And those are three different types of boundary conditions. We could, of course, have other types of boundary conditions, but those are just three categories that we're going to explore in the near term. And finally, we need initial conditions. U of x, comma, t equals 0 is equal to f of x. With these three together, we can then determine solutions. Okay, so together we're getting a better sense now of what PDEs are and the types of information and data and the means by which we can solve them are. So with that, I'll leave you to do homework.